the message of this lecture is as follows, that if we have an analytic function defined in a simply connected domain, then this analytic function has antiderivative and its contour integral is independent on path, and its loop integral along a closed contour, is 0. So today we will talk about one of the important theorems. They all are important in complex analysis. This is the Cauchy-Goursat theorem. So Cauchy-Goursat theorem. So let's first write the formulation of the theorem and then we can discuss it. So a theorem. If a function f of z, if function f of z is analytic, at all points interior to and on a simple closed contour, let's call it C. Then integral along C of f of z dz is 0. So let's maybe talk about terminology first. So simple, right? It means that it doesn't have self-intersections. So this is not a simple contour because it's self-intersect. And closed, it means this is a loop, right? Loop, it means that if we parameterize this contour and introduce some parameterization, then our initial point and terminal point will coincide. So we have a loop. So this integral equals to 0. So before talking about the proof of this theorem, let's try to make connections with what we discussed in the previous lecture. So in the previous lecture we reviewed the fundamental theorem of calculus, and one of the versions of this theorem was that if we have a gradient field, then line integral of a gradient field doesn't depend on the path. So if we have line integral and we have here a gradient field, let's say gradient f dot with ds, then it doesn't depend on the path, so we can take one path or we can take another path as long as they have the same initial and terminal point, right? So if we have initial point and terminal point, and if we have one path C1 and if we have another path C2, then both integrals are equal. And from here we can see one more thing. So if point A, point B. If this integral is equal to integral along this path, then it means that what happens if instead of this path C1, we will trace it in the negative direction. So since they both equal, it means that then we will have that integral along C2 plus integral along negative C1 will be equal to 0. And here what we will have, then we will have a closed loop, and we will see that, and we see that integral along closed loop of a gradient field equals 0. And my goal is to show connections between this fact and what we have here. So there is another formula, Green's formula in vector analysis, that can show us that integral of gradient field equals to 0. So let's review this formula. Okay, so let's recall the Green's formula. So to recall the Green's formula, suppose that we have a simply connected domain D. So a simply connected domain D, by that we mean that if this is our domain D, simply connected, it means that if we put here any contour, it will be surrounding only points in D. So in other words, there are no holes. So if we have such a domain D, right, its boundary DD, let's call it C, and then the Green's formula tells us that integral along the boundary C, line integral, where we have P of x, y, dx plus Q of x, y, dy equals to double integral over this domain D, and here we have dq dx minus dp dy dx dy. So this is the Green's formula. And we can look at Green's formula. And we can look at this line integral as a dot product, right? Of when P and Q, we can think of P and Q as a vector. So if we think of them as a vector F with components P and Q, and then let's assume that vector F, vector field F, is a gradient field. That is that P and Q are partial derivative of some function phi. So this is equal to a gradient of some function phi. Then what will happen? Then if we put here instead of P, if we put this is phi x, right? Phi x, derivative of phi with respect to x. Q is derivative of phi with respect to y. Then here, what we will have? We will have phi x y minus phi yx, and if we assume that phi is continuous with continuous derivatives, then that would be just 0, right? So then this integral would be equal to 0, and also the first integral would be equal to 0, and then we will see that integral of gradient field along the loop is 0. Okay, so now let's use Green's theorem to sketch the proof for Cauchy-Goursat theorem. So let's read Cauchy-Goursat theorem again. So if we have a function that is analytic on a simple closed contour, right? So we can think of this contour C, and then integral along this contour C of analytic function is 0. So let's memorize what we're trying to prove. And just let's apply Cauchy-Goursat theorem. So we can rewrite integral of our function f of z dz if we say that real part is u and imaginary part is v, and for dz we have dx plus I dy, then we can rewrite our integral as two real valued line integrals. Then we will have, first it will be integral u plus I v dx plus I dy on contour C. So the first integral we will have u dx minus v dy plus second integral along C. Second integral with I, we will have v dx plus u dy. And now let's apply Green's theorem to each of these two integrals. So now if u acts as p in Green's formula and negative v acts as q, then we will have double integrals. We'll have double integral. So we have dq dx, it will be negative vx, and then minus dp dy minus uy dx dy over d, and plus I double integral. And now this is our p, this is our q, so we will have vx minus uy dx dy. And now let's recall Cauchy-Riemann conditions. So we have our Cauchy-Riemann conditions saying us that ux equals vy and uy equals negative vx, and that will give us the following. So we said that uy equals negative vx, so here we'll have 0, and here vx equals uy, so here we also have 0, so the entire integral would be 0, which will finish the proof. Okay, so now let's discuss some generalizations of Cauchy-Goursat theorem. So first generalization would be, let's call it theorem 2, generalization of Cauchy-Goursat theorem. Previously we said that a contour must be simple, but this is not really important. So we can say that if a function f, of z is analytic throughout, throughout a simply connected domain D, simply connected domain D, then integral f of z dz equals to 0 for every closed contour C in D. For every closed contour C in D. And this is really easy to see. Suppose we have our simply connected domain D, domain without holes, and we have some contour, right, that has some self-intersections. We can call this contour C, and suppose that we started going in this direction. We'll go in this direction, go, this direction, and then we're going back, right? Then we can see that we can look at this contour as a sum of contours. So let's look at this contour, this one, this part, right? Let's call it C1. And then we can call the next to it, next loop, C2. And then this would be C3, this would be C4, and this would be C5. And each of those small contours is a simple closed contour, so integral along each of the contours would be 0, so the sum would be 0 as well. Right, so this was a generalization of Cauchy-Goursat theorem. So now let's make a remark. What if our domain is not simply connected? So remark. So what if we have a multiply connected domain? Multiply connected domain. So let's think of a domain that has a hole, right? So this is our domain. And then if we take two contours that are homotopic to each other, so if we take, for example, contour C1 and contour C2. So what does it mean homotopic? If they can be continuously deformed to each other. So basically here they surround the same hole, they can be continuously deformed. Or these two contours, right? So we have C3 and C4, they also homotopic to each other. So here we know that if we look at these contours, we know that integral of analytic function will be 0 according to Cauchy-Goursat theorem. But what can we say about integrals along contours C1 and C2? These two integrals would be equal to each other. So integral of an analytic function f of z dz along C1 would be integral along C2 of the same function f. So how we can see that? If I draw these two contours, so let me make a zoom. So this is, suppose this is C1 and this is C2, and now let's make a cut. Let's introduce also contours here, C3, which going in this direction, and really close to it. So it's one cut but two sides. I will put two lines, so this is C4. So they really next to each other, different sides of the cut. And then let's look at this domain that is enclosed by a contour C. Let's look at contour C. That is a sum of C1 plus C2 plus C3 plus C4. Right? So let's look at this contour. And now if we look at the integral along contour C of our function f, analytic function f dz, then our function is analytic everywhere here. If we go first along C1, then along C3, then in negative direction, negative C2, negative C2, and then back to C4, we will enclose this area, and the integral, so we will have that integral along this area of an analytic function, right? So basically what happens when we cut this this domain here, we can split it, kind of split it, so we can deform this domain into something like that, where here, say we have C1, this part would be C3, this would be negative C2, and that would be C4. And this would be our domain. So obviously this integral along this contour is 0, and since this integral equals to 0, and if we look at the integrals along C3 and C4, it's basically we're computing an integral along the same line in different directions, so they both will be cancelling each other. So we will end up with this expression that integral along C1 equals to integral along C2, because integral along C1 minus integral along C2 is 0 from this consideration. And what is another thing that we can get from here? If we have, suppose we have a multiply connected domain with many holes, then similarly what we can get. So if we have a multiply connected domain with holes, and if we're considering integral along some contour C, this would be our contour C, and then we can deform our contour into something like that. And then finally we can move these two sides closer to each other. So basically then there will be something like that. And here and here, right? So these two integrals along these sides, it's going in one direction, in the other direction, so they will be canceling each other. So finally we will end up just with integrals along small circles. Say, let's call it C1, this circle let's call C2, and this, or not necessarily circle, this small contour C3. So we can write a formula as that integral along C of a function that is analytic in this multiply connected domain, dz, would be equal to a sum of integrals along ck, if c1, c2, c3, if we call them ck, f of z, dz, and k equals from 1, no, let's say to some number m. So this was another generalization that we can discuss. So let's continue further. So let's mention one more theorem that is related to Cauchy-Goursat theorem. We will mention this theorem without a proof. You can find in Conway's book. So the theorem 3 would be that if D is simply connected, if D is simply connected, and function f of z and f of z is a function that is defined in D, it's complex valued function, and if this function is analytic, in D, then in D f of z has antiderivative. Then f of z has antiderivative in D. Has antiderivative in D. So now let's consider some examples, right? So what we are trying to discuss in this lecture, we're trying to talk about the fact that if you have an analytic function, then integral along a loop is 0, then integrals along different paths having the same initial and terminal points are equal to each other, independent on path, and analytic function has antiderivative. So let's look at the first example. Let's look at this example. Example 1. So let's just compute dz over z, and here will be a contour, some contour, and this contour would be this. So it's a contour that joins points negative 2i with point 2i, negative 2i with point 2i, and this is some continuous contour. And this is a good contour. So then, how we can compute this integral? So the first way would be, since we mentioned that it's only important the initial and terminal point, so we can replace this contour with a circular arc. So we can replace it with a circular arc. Oh. Let it be traced in the same direction, so it would be a counterclockwise direction. And we know if we have such an arc, then z along this arc would be equal to z equals 2 e to the I theta, and that would be our parameterization, where theta is running from negative pi over 2 to pi over 2. And then we will have integral from negative pi over 2 to pi over 2. So we will have z in the bottom to be 2 e to the I theta. dz would be 2i e to the I theta dz. Then 2 times e to the I theta would be cancelled, and we will have just I theta. Integral would be equals to I theta. Substitution from negative pi over 2 to pi over 2, which would be equals just to pi I. Right, this is first possible way to compute this integral. And also, if we want to use antiderivative, then we can compute the same integral the following way. So let's call it first way, would be first way, and then look at the second way. We can compute this integral. So we can compute this integral using antiderivative. Then we can notice that integral along C dz over z, we can introduce a cut here, think about the cut. So we can say that 1 over z is derivative of the principal branch of logarithm. So 1 over z is derivative of the principal branch of logarithm, log z, so antiderivative would be log z, and then we just evaluate this function at points of negative 2i and 2i. So then we will get, when we plug 2i's, modulus of 2i's is just 2, so we will have ln of 2. What is the argument of 2i? Argument of 2i is pi over 2, so plus I pi over 2 and minus, here modulus of negative 2i is still ln 2, and the argument is negative pi over 2. So negative I pi over 2, and then just ln natural log of 2 will be cancelled out, and minus will give us a plus, so we will have again pi I. Obviously, if we do everything correctly, we will get the same answer. So this was the first example. Let's look at another example. So if we have another example, so example 2, so you have to determine the value of this integral. So if we have integral along a unit circle, say of this function z e to the negative z dz, find the value of this integral. So evaluate this integral. So we can look at this integral and see that z is an analytic function, e is to the z is also analytic function. So here we have an analytic function, and according to Cauchy-Goursat theorem, we have integral along a closed loop, right? So we have here we have our unit circle, so integral along this unit circle, and we can assume for definiteness that integral, this is the circle traced in positive direction, so counterclockwise. So this integral of analytic function along the closed loop would be just 0. This was another example. So what was important in this example, that we had an analytic function. Let's look at another example. And compare with this example. So again, evaluate. This would be example 3. Evaluate the following integral. So let's take integral along some circle with radius r, traced in a positive direction, and let's take z bar dz. So the first question would be whether or not this integral equals to 0. And here we cannot expect 0 because z bar is not an analytic function. So since it is not an analytic function, we do not expect here 0. So what we can do, we can use parameterization. So parameterization is a universal method, right? We can compute integrals of both analytic functions and functions that are not analytic. So what we can do, we can introduce parameterization of these circles. So we assume that z equals r e to the I theta when theta runs from 0 to 2 pi. Theta runs from 0 to 2 pi. And then our integral will be, so we have integral from 0 to 2 pi. Z bar then becomes r e to the negative I theta, and dz would be r I e to the I theta d theta. And then we will have e to the negative I theta and e to the I theta will give us just 1, and r squared I can be pulled out, so we have r squared I integral from 0 to 2 pi d theta, and this integral obviously will give us just 2 pi, so we will have 2 pi r I, r squared, right? So then we can, if we recall that pi r squared is area of a circle, so it will be equals to 2I times area of a circle. So area surrounded by our contour. That was another example, so I will stop here. Thank you.